and we go, right? So we pray that this is a good class, that all our students stay attentive, and that everything goes well. In Jesus' name, amen. All right, so we have an objective here, and it's just mostly a discussion objective. I'll share my screen in a second because I know you're not seeing my screen. All right, we want to just talk about the general properties of algorithms. More like a 2-minute chat. Oops. It's not what I wanted to show. Okay. All right, so everybody is with me. All right, so we have the necessary properties of algorithms that are well designed. And what are the necessary properties of algorithms? This is straight from the syllabus, eh? Okay, so this one is not anything special, right? This is straight from the syllabus. When we look to solve a problem, and we've already established that we can utilize algorithms to solve problems. In terms of our problem solving, and we want to be able to define what an algorithm is. And can anybody as well define what an algorithm is for me? I mean, I know that you know, because I know that in Form 5 you would have had to write an algorithm. So anybody can say, what is the definition of an algorithm? Don't all put up your hands now.
It's a series of steps.
Right. So I heard a series of steps from somebody. I see Clement and Real with their hands up. Let me see who. All right. So actually, Hansen had his hand up first. So Hansen.
An algorithm would be like a series of steps used to carry out a specific function.
Right. Okay. That's good. A series of steps to carry out a specific function. To what end? So next person in the queue. To what end? Real.
I was going to say the same thing.
You were going to say to carry out a specific function.
Yes.
All right. Okay. So the specific function that this algorithm carries out is to, Clement, you want to suggest something?
So I was just gonna add certain set of instructions given to a computer to carry out some instruction.
Well, not necessarily a computer, because we could follow an algorithm, right? We could follow, think about it like a recipe, essentially, is an algorithm. So a recipe from a cookbook is an algorithm. So Real.
A series of steps taken to solve a particular problem.
Right, that part I was looking for, right? So I'm happy with the series of steps. So an algorithm, right? An algorithm is a series of steps that, when followed, solves a particular problem. Okay, and it comes back to what I was saying just now. It comes back to what I was saying just now in terms of being able to, not just say carries out a function, because carry out a function doesn't give me, it's inclusive, but it doesn't give me the answer that there was a problem, and at the end of this algorithm, there should be no problem again, or there should be some resolution to the problem. You guys follow me what I'm saying?
Yes, sir.
Yes, sir.
Right.
Yes, sir.
Okay, good. So All right, so we're looking at focusing on algorithms. So what we want to create algorithms, and we want to create algorithms that are considered well designed. We want to create algorithms that are considered well designed. And as I said last class, we took a look at the problem solving process, and we know that within the problem solving process, one of the things that we have to do is when we come up with this overall or big idea in terms of solving the problem, and we evaluate that big idea in terms of solving the problem, we have to come up with a series of steps that will allow us to solve this particular problem. So the thing is, the series of steps that allow us to solve this particular problem need to be well designed. And so we have to understand the general properties of any algorithm, any series of steps that we are following. Okay, so we have these 4 characteristics that are on your screen right now. We have that the algorithms, the necessary property of algorithms are that they provide a general solution to a problem. Okay. When we say a general solution to a problem, we essentially mean it solves the problem in its entirety. All right, we solve the problem in its entirety, or at the very least, there is very little left back to solve. Right, but a general solution, you should no longer have any sort of problem. So again, with the example that we used in class last day, like the hole in the roof, and we got 2 different suggestions. We got one where you can hire a professional, and we have another one where you could fix it yourself. Fixing it yourself might not really provide a general solution to the problem if it is that you are not versed in, attempting to fix things like a hole in the roof, or you're not a handy person or something like that, right? Because at the end of the day, you might get a partial solution to the problem. You mightn't get sun coming in your house, but you certainly might still get water or rain coming in your house. Agreed? Whereas the person who is professional with it, after they fix your roof, no sun, no rain, no critters, no nothing crawling inside your house. That's general, covers a series of areas. Next up, for the necessary properties of algorithms, we need to have clearly defined and unambiguous steps. What does that mean? Anybody? When I say that, and there's the inflection, as I said, that's a question to you. What does that mean?
So it means that I have no room for interpretation or mistakes.
Correct. Okay. So when a step is given, it should be understandable. We should be able to identify what to do in terms of that, that step or that task that needs to move us towards getting to our solution. It have them, it have those people who sometimes you're driving around and you're lost, and you stop and you ask somebody and you say, hi, I'm looking for my friend Rampasad house. I think a little lost. You know the person, he say that, he living on so and so street. And they say, yeah, man, just drive 5 minutes ahead. Look for the big tree, not the big tree, but just the big tree. And when you reach by the big tree, you go see a group of boys lying there, because them always lying there, and you go ask them for Rampasad place, and they would tell you, right? They go say go down the track and you go find Rampasad place. Did that person give us a general solution to the problem using clearly defined and unambiguous steps?
No, sir.
No.
Not really.
So I can imagine a Trinidadian actually saying something like that.
But that is I'm telling you, right? I know Trinidadians. When I was in secondary school, some tourists stop a friend of mine and ask them how to drive to Tobago, and he gave them instructions to do that. Right? So I know Trinidadians. All right. So the thing is, a lot of those steps, they're not clearly defined. They're dependent on something. Which tree is the big tree as opposed to the big tree? Does this tree have a type? Right? When you say just drive down the road for a little ways again, how much is a little ways? 3 minutes of driving, 5 minutes of driving, at what speed? Right? At what distance? Okay? What if the boy's not there at that particular time to give you more information on reaching to your friend's house? So, you know, there's a lot of you know, unambiguous steps or unclear steps or things that you're not sure about in that little story there. And again, the third property, right? Sorry, moving on, the third property of a well-designed algorithm is that you must have a finite amount of steps. And that makes sense, because if you don't have a finite amount of steps, what happens? If you don't have a finite amount of steps, it means that eventually, yeah, right? Eventually you get either fed up and decide, well, this thing not bringing me to a solution, or it'll take forever, you'll never reach to your solution. So we need to have a finite number of steps. Sorry, all right. And the last one is flow of control from one process to another. This one, kind of wondering if anybody could define this one for me. Let me see if you all understand what a flow of control means from one process to another.
So like you're just jumping all over the place. You don't really
Yeah.
have like a structured flow of like things are gonna happen. So like when you're giving instructions, instead of telling someone take up a pen and put the pen on the paper and write away, you're telling them like take up a pen and throw it in a bucket and then write a word on the book. And it's not really making sense and the steps not really logical in a way. So
Right.
yeah, I think.
I agree with you, right? I like what you're saying, right? And it doesn't even have to include illogical steps. It just might mean that the steps are not in the order that makes sense. So if it is that I am looking to bake a cake, the first step shouldn't really be place the pan with the cake mix in the oven. Why is that? Because then the second step you tell me is to crack 2 eggs into a bowl, and then you say add flour, and then you say, you know, sacrifice a chicken or something, so right? And tell me, you all don't sacrifice a chicken when you're making cake? No? Nobody?
No, so I do know.
Sometimes it
Sometimes, right. I
If
mean,
your body cake tastes good now, so you understand?
exactly. If you don't do that, then the cake never tastes, you know, what's up. So, all right. But generally, once you have a series of steps, the steps must make sense. And it means that you need to be able to do a step, finish a step, and take the output of that step as the input of another logical step in the series of steps in the sequence towards your answer. Okay, I'm going to say that again. You're going to have to complete each step, get the output of each step, and that output of each step can act as the input to the next step that is going to allow us to eventually get to our solution. Okay? So In the event of an algorithm, yes, sometimes some things can run concurrently, and other times some things don't. Okay, sometimes you have to finish one task before you can move on to another task. So in terms of the cake, because the cake seems like a decent example to use, right? Sometimes cake recipes might assume that the amount of time that it will take to preheat the oven, you can do other things. So the first step that you might see in making a cake is preheat the oven to 350 degrees Fahrenheit. Then they would say, gather all the ingredients and, have them prepared and ready to mix into a bowl according to the measurements, right? So you'll put your half stick of butter, your 2 cups of flour, your sugar, your cup of sugar, and maybe your 2 eggs, and mix them. And the thing is, you really and truly can't be you can't be putting in, or you could, depending on how skilled you are, you could throw in 2 ingredients at the same time. But the thing is, the mixing of the ingredients could take place at the same time that the oven is being preheated. But what cannot take place at the same time that all the ingredients are mixed, are going into the same bowl is that you have to mix them, with they say whisk all the ingredients together. That is something that depends on the previous sets of instructions being completed. So that is where flow of control comes in with respect to algorithms. Everybody's good there? So
Yes, sir.
why am I saying this? Because we have to keep these things in mind when we are creating our algorithms. All right. I know that we haven't really gone into algorithms. We just spoke about problem solving. We did a little bit of what you call it? Speaking about the truth tables and logical operators, etc. But we are on the verge of approaching or attempting algorithms, and we need to know the rules and we need to know what algorithms are. Okay. And the next thing that we have is that we have 3 different ways of representing algorithms. So we can represent algorithms in 3 different ways. And again, I'm going to pull it directly from the syllabus. And the 3 ways of representing algorithms include narrative. And narrative involves essentially expressing the steps to follow in plain English, either written or spoken. So the narrative is, plain English. You're just gonna draw a line and so this is plain English. We just speak it out if it is that you are giving instructions in natural language. Narrative is not really, it is the furthest from computer executable code, right? Maybe one day we will get there where we could just tell our computer systems to do something and it will do something. And we are getting there slowly and slowly with, things like that, Google Voice Assistant and Cortana and Siri and stuff like that. But, for now, narrative is mainly so that we humans could interact with each other and give each other instructions, etc. The next way of representing algorithms involves flowcharts. Flowcharts are diagrammatic representations, right, of algorithms. And within flowcharts, we have some symbols. We have some symbols that will allow us to be able to, we have some symbols that will allow us to be able to, indicate, well, different behaviors. Okay, we'll take a look at how to start a flowchart using a symbol, how to stop a flowchart using a symbol, how to call a different process, how to make a decision using a flowchart, and how to loop instructions, etc. Okay, and lastly, we have pseudocode, which is like structured language, right, to represent instructions. And I'll put in brackets here, computer-like. Computer-like, okay? So your pseudocode algorithms are not meant to be read by and executed by computers. Your pseudocode algorithms are to be, they're to be, used to model the computer-like structure. And again, this is more of a something that could be used between computer professionals who are developing an algorithm or developing a system, and they want to, maybe they don't know which particular computer language they are going to create the system in, or maybe they might have to use different languages. But pseudocode is kind of like a common language that multiple developers can use to represent their ideas about development of a solution. Okay, so it looks like something that could be executed on a computer, but let's say, for instance, Anaya knows C and Jeremy knows Java, right? And John Michael knows Python. And they just want to brainstorm with each other at a point to come up with a solution for a particular problem that is eventually going to be executed on the computer. What they can use to pass and share information among themselves is pseudocode. So it essentially can be translated by a programmer into any language, but it is not in itself a particular computer language. Everybody is with me? Yeah, all right, good. You have any questions up to this point? Comments, any questions? All right, so we good. Right. So just moving on, take 2 minutes, breathe. Let me just pull up the next thing that I have to pull up. Right, so far we've spoken about the properties of algorithms, we've spoken about ways of representing algorithms. And we have different constructs with respect to, creating algorithms. And well, most of you all could tell me the construct, I believe. I think I asked you this already, right? So we have programming constructs. And could anybody remember or tell me what are the programming constructs that exist?
So the programming constructs are like the or and the and the
No, those are operators.
Oh.
Right. The programming constructs, they allow us to structure programs. They allow us to structure programs to be able to express, our logic and work through our logic to be able to achieve a particular task. I don't know if anybody is.
So is it the one with sequence and selection?
Yes. So we have sequence, we have selection. And we have the last one. Anybody remember the proper name for iteration? So we have sequence, selection, and iteration. And sequence is essentially what we spoke about just now. That last property of good algorithm development, which kind of, well, it is kind of like the second and the fourth property when you think about it together. Sequence is the logical flow of execution of your program. So sequence speaks to the logical flow of execution in a program. Right? And I'll use the words program and algorithm interchangeably sometimes. So know that, you know, all programs involve algorithms, but all algorithms are not programs. Okay, because you could have pseudocode algorithms, you could have flowchart algorithms, etc. So we have the logical flow of execution in a program or algorithm. Selection is essentially how your program makes decisions. So selection is decision logic within an algorithm. Decision logic within an algorithm. And then iteration is basically repetition, or for those of you like me who cannot spell the word repetition on camera without embarrassing himself, looping within, all right, looping instructions within an algorithm. So we have sequence, selection, and iteration. Those are our three main programming constructs that allow us to be able to, that will allow us to be able to control how our program works. Okay, and I'm going to put a nice, much better written structure here, right? Definition here. And so we say that the sequential logic structure, all of your programs must, the iteration and the decision logic, those don't exist in all of your code. But sequence must exist in all of your code because your code must make sense logically, right? So it is no matter what you write, your program must make sequential sense. And then, of course, the second thing that we use is that we use the decision logic structure, right? Oh, I forgot to copy the names of the structures. Sorry, I'll put that on top. All right, the program uses the decision logic structure to make decisions, to make choices. So what we end up getting is that we end up getting a choice. And that choice is based on some condition being fulfilled by the computer system. And the last structure is looping, which I said repeats. It's repetition. And that repetition is, again, either based upon the satisfaction of some criteria, or it's based upon some preset value in which we want to loop. Okay? And the thing is, everything in computers, from the little programs that we write now, learning how to do C, right up to the most fancy of operating systems, all of them incorporate these principles, these three principles. So it does not matter whether you're doing programming for the web, or if you're doing creation of operating system, creation of application software, creation of embedded software. Once you are doing programming, right? Once you're doing programming, yeah, iteration is looping, sorry. Once you are doing programming, then you have to follow these rules. All right. Let me put the names of them here as well. I didn't copy the names. So I'm putting them inside here. Okay. We're going on. So we want to take a look at least programming with sequence today, right? With at least programming with sequence today. And once we start to program, actually, let me take a step back. Once we start to program, there are some things that we need to know. All programs and all computer systems follow these basic behaviors: input, processing, output. Okay. Now, again, what I'm saying here to you today, these might seem like very simple concepts, but these concepts translate right up to the most complex levels in computing. But these are the rules of computing. Everything that we've said here today, in terms of the properties of the algorithms, not the ways to represent it, of course, but the structures, and now this input, processing, output. These are the rules behind computing, right? And of course, we could have storage being here interacting with processing. And these are the rules of our computing. Every program that we will write follows this basic rule here. Okay. So bear that in mind. Every program I have to write, I have to ask myself, what are my inputs? What are my outputs? What do I hope to get out of this program? What do I need to put into this program to get that out of this program? And the processing is essentially the steps that would allow me to get from my input stage to my output. The storage is it is my variables, right? So the storage is what can I use to keep information and manipulate that information so that I am going to be able to get to my end goal, my output, my program. Okay? You're all looking at me, and I feel like if you're saying, hey, stop talking and just get to the programming. That's what we're here for, right? But I have to lay down these rules. All right. So in terms of, and just looking at input and output, for doing our algorithms, of course, right? When we want to get a value to get, or let me type it up because it'll seem better typed up, right? So I want to talk about getting a value from the users, and I want to talk about printing out a value to the user. So get a value from the user in an algorithm, we can use the input statement. Input or read statement. Okay? So for example, if it is that I wanted to, let's just go with a very basic program. We want to have a program that will allow us to print out the area and circumference of a circle, right? The area and circumference of a circle. What input would I need to be able to get the area and circumference of a circle?
The radius.
The radius. Okay. So for example, I would start off by saying input R for radius. But how do I know what R is? What can my radius be? My radius could be some value. Is it an integer or is it a real number?
It would be a real number.
Right. Yes, it's okay to have it as a real number. So to start, we will declare the variable. And we have to declare a variable. And you don't have to put them in caps. I just putting them in caps for emphasis right now as we learn it. Okay? So to declare the variable, we say real R. And that R is going to be, R represents the radius value that the user will enter. Then to get the variable from the user, use the input statement. Okay, so we say input R. What does that tell me? It tells me that my algorithm, if it were executing on a computer, it will be waiting on input from the it will be waiting on input from the user. So the user will put this input in and it will store in the variable R. So the first thing is that we could always think of our programs as what are my inputs, what is my processing, what is my output. When we start to decompose, algorithms as well, we'll do the same thing into functions. Each function is going to have a section where these are my inputs into the function. This is what the function does. This is what the function outputs. And we're going to call those inputs parameters and we'll call the outputs return values. But it's the same concept. And this is why I keep on stressing that in the back of your mind, all you need to know to be a computer professional, or let me say a programming professional, is to think about input, processing, output. All right, what are my inputs? What are my tasks? What do I produce? Okay? And you could apply that to your student life, right? As I said last class, I'm teaching all your life skills here. All right. So, you know, when you get a nice hard assignment, you'll be like, wow, what are the inputs for this assignment? What am I supposed to do? And what should I produce? Okay. All right. Mr. Valdez, computer science teacher / guidance counselor. Right? All right. I seem like the only one having fun here. Everybody else's face is just straight.
So what you mean I have one more stand off here? Come on.
Oh gosh. All right. So right. So we see the example for the input, and then we move on to the processing. Then we move on to the processing. So the processing is what will get us towards that output that we will produce. So the processing involves some statements. The processing involves some statements. The processing involves being able to do some calculations. So what else would we need in our processing? We need to store some values here. We stored some values upon input, but we also need to store some values during our processing, because we can have the value of let's name it circum, because I can't remember how to spell the whole word. Circumference, and then we have a nice easy word, area. Okay, so we have circumference and we have area also, and those variables are now there to assist us with the processing, because when we process our information, we need to have some value to store that information in. Okay, and then we also have, of course, constant real pi. Okay, is equal to 3.14. All right, so we have pi, and then we could say CIR/CUM is equal to, circumference is what, 2 pi r, 2 multiplied by pi multiplied by r. And what do we get there? We get the circumference. We do this here is processing. This one little statement here is processing. We have area. Area is equal to pi multiplied by r to the power of 2. So pi r squared. And then the last thing that we do is to print out to show what we want to print out to the user, right? To show what we want to print out to the user, we use the output or print. So what we want to print out to the user, we use the output or print statement. You can use them interchangeably, but I would suggest that you use them consistently through any one program. So don't have output here and then print later on. Okay, if you choose to use output, use output. If you choose to use print, use print. Agree on that? Great.
Yes, sir.
So,
Wonderful. So, print, and we could say print the, and when we are outputting, we have something called a string literal. You see things between these quotes here, things between those quotes, print as you type them or print as you write them. This is called a string literal. Okay? So within the print statement, we have two things that we can have. We can have variables in the print statement, which will print the value represented by the variable, or we can have the string literal. So if I type the area of the circle with the area of the circle with the radius, and I want the actual radius to print out, I have to put the variable there, r. And then I want the word is, and then I have the actual circumference, right? CIR/CUM, CIR/CUM. Okay, so the area of the circle with the radius r is circum. But when this prints out to the user, it prints out the value inside of R, and it prints out the value inside of circle. Now notice that after the word radius, I have a space, and I want that space to print out. Because if I don't have that space, the value for R is going to print right next to the word radius. Okay, I have a space before the word is. Why? Because I need that space to print out. I don't want the word is directly following the value of R. So if R was 5, I don't want to print out the area of the circle with radius 5 is, and leave out my spaces. All right, okay, no problem. So I see, I like that. Any questions so far?
So you just need to change the circum to area.
Oh, my bad. Oh, that's, and nobody told me anything earlier, so I was there yapping on about it, and you know, all right. But y'all know what I meant, and we doing the same thing for circumference. All right. Circumference of the circle with the radius R is, and now if we were to run this, if we were to run this here, you know, as in if we were to read it and execute it, and actually kind of, you know, think to ourselves, well, we're going to draw the variables, and we're going to draw the variables and do the show what is going to be stored inside of each one of these things. Then we can see it in action, because this is a pseudocode algorithm. We cannot do this, you know, on any computer system. But eventually, we will be doing things like this up in the C programming language, and we will be able to execute and test it. So for now, we have enter input value into the radius. So we have input R. Let's say, for instance, we had a circle with radius of 9.7, right? 9.7 is going to be associated with the variable R. So what does that mean for the next couple lines? We're going to have a variable named circum and a variable named area. And what do we want to do? We want to calculate circumference. Circumference is 2 multiplied by 3.14 multiplied by 9.7, right? We're going to get the value of 60.916 inside of it. And then the system will move on and calculate the area of this circle, right? So we get 3.14 multiplied by 9.7 multiplied by 9.7, and we're going to get 295.4426 inside of it. And so what is going to happen when we print out our output? Our output itself is going to look something like this, right? Our output on our screen, and sometimes I just like to draw the screen just to, you know, just because using your imagination is magical. Okay, so what is going to come out? The quotes aren't going to come out, but the text is going to come out. The area of the circle with the radius, not R, sorry, but R is 9.7, is 295.4426. 4426. Okay? Any questions so far? All right, so here's what we're going to do. We're going to take 10-minute break. It's 1:55. We're going to take 10 minutes, get some water, get up, stretch, use the bathroom if you have to. I'm going to pause the recording. When we start back, I'm going to resume the recording. And we will, we will continue on with what we're doing. So far, everybody's good, right?
Yes, sir. Yes, sir.
Yes, sir.
Yeah.
All right, great.